This model of the atom is in fact in today's popular culture one of the most famous models of the atomic structure because it gives you a very simple picture of how the atom is supposed to look like according to Rutherford. So the circumference is equal to an integral multiple of the wavelength of the electron, which now tells us why this condition exists in the first place. So basically, the orbit of the electron in a hydrogen atom corresponds to one complete electron wave joined in itself. Almost 150 years back, scientists were convinced that matter is not continuous but made up of discrete particles or atoms. But what is the nature of these atoms? What is the structure of these atoms? These questions were still unanswered. After the discovery of the electron by JJ Thomson, it became quite clear that there are particles called electrons which are very light and negatively charged. But atoms themselves are neutral particles. So JJ Thomson gave his atomic model in 1898 in which he suggested that atoms are just lumps of positively charged matter with negatively charged electrons embedded in them so that overall the atom is neutral. Alright, so imagine like a cake with chocolate chips embedded in them. So that was the very first model of an atom suggested by JJ Thomson. However, further investigations by Rutherford and his team in 1911 gave a completely different picture of the atom. What Rutherford and his team did was they bombarded alpha particles onto a gold foil. Now alpha particles are essentially helium nuclei. They are heavy particles traveling at very high speeds. When they are incident on a very thin gold foil, it was found that vast majority of these alpha particles penetrated through the gold foil undeflected. Some of them were deflected by large angles and a very minute minority of them were in fact deflected in the exactly opposite direction. This was a very surprising result because alpha particles, as I said, are positively charged, quite heavy and traveling at very high speeds. In the words of Rutherford, it was as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Because majority of the alpha particles went through the gold foil undeflected, he assumed that vast majority of the atom is in fact empty space, and because a very tiny minority of them were actually reflected backwards or deflected by very large angles, he assumed that the vast majority of the mass of the atom is concentrated at the center, just like the model of the solar system. So in the solar system, you have the sun at the center and the planets revolving around it. So Rutherford gave his planetary model of the atom in which he suggested that the vast amount of the matter of the atom, which is positively charged, is concentrated at the center, and these negatively charged light electron particles revolve around the nucleus because of electrostatic forces of attraction. This model of the atom is in fact in today's popular culture one of the most famous models of the atomic structure because it gives you a very simple picture of how the atom is supposed to look like according to Rutherford. So Rutherford gave his planetary model of the atom. And in this planetary model, what you essentially have is you have an electron which is going around the nucleus in orbit. So essentially you say that if we have a hydrogen atom, the hydrogen atom has one electron and one positive charge. So essentially a proton. The entire mass of the hydrogen atom is concentrated at the center, and then you have a very light electron, a negatively charged and a very light electron going around in orbit around the nucleus, just like the planets in our solar system goes around the central sun, which is the star. Now we can apply the ideas of classical physics, essentially the balancing of forces, of electrostatic forces acting between the positively charged nucleus and the electron, and figure out some expressions regarding the radius as well as the total energy of this kind of a system. So let's suppose that the radius of this kind of a configuration for a hydrogen atom is given by R, alright, and then we have these various forces. We have the electrostatic forces of attraction, alright, and the centrifugal forces because of the revolution of the electron around the proton, and then we can apply the balancing of forces. So for example, we can first look at centrifugal force. Alright, so centrifugal force arises as a result of the revolution of the electron around the nucleus, which says that the centrifugal force is simply equal to mv square upon r. Here m is the mass of the electron. Alright, so this is the mass of the electron, and we have electrostatic forces of attraction, which is essentially E square, because the atom itself is neutral, so the electron charge and the proton charge should be exactly equal in magnitude, but opposite, of course, in terms of this is negatively charged and this is positively charged. So E square upon 4 pi epsilon naught r square. So this is the Coulombic law for attraction between two electronic charges. Now, if we have some kind of a balanced configuration, then these two forces must be balanced. So by applying these balance of forces, I say that Fc is equal to Fe. So therefore, mv square, where m is the mass of the electron, v is basically the orbital velocity of the electron around the nucleus. Keep in mind that this is a classical model of the atom. Alright, so I'm trying to derive these expressions based on a classical model of the atom right now. Okay, then we'll see later on what happens. So mv square upon r is essentially equal to E square upon 4 pi epsilon naught r. So from here we can get an idea about what is the orbital velocity. So the orbital velocity essentially comes out to be v is equal to, so this is r square, so E square upon 4 pi epsilon naught m r, alright, root over. So this is the orbital velocity according to the classical picture of an electron going around a positively charged nucleus, just like planets go around the sun. Now, what about the total energy of this kind of a configuration? We can calculate that also. So just let's do that here. So if I want to find out what is the total energy of this system, then based on this very simplistic model of the atom, it has kinetic energy and it has potential energy because it is in this kind of a electrostatic potential. So the total energy E is equal to kinetic energy plus potential energy, where kinetic energy is equal to half mv square and potential energy is equal to E square upon 4 pi epsilon naught r. But we know that v square is essentially equal to this times square. So if I make this substitution here, if I just make this substitution here, I should end up getting half m times v square is equal to E square upon 4 pi epsilon naught mr minus E square upon 4 pi epsilon naught r. So here m and m gets cancelled, and essentially what are we left with? We are left with this final expression for energy. The total energy of the system is equal to minus E square upon 8 pi epsilon naught r. So this is, there you have it, based on classical ideas, the total energy of a hydrogen atom that we have obtained. However, this kind of a model that Rutherford provided was not really sufficient from a scientific perspective, and I'll come to that why. So first of all, this is the orbital velocity that we have obtained, and this is the total energy that we have written down here. Okay, total energy. Now, what were the problems related to this kind of a Rutherford model? The problem is quite simple. You see, based on this particular derivation, we have basically applied Newton's laws of classical mechanics, which is one of the strong pillars of classical physics. However, we are dealing with a charged particle here, and even though this model is in sync with the Newton's model of mechanics, it is not in sync with electromagnetic theory. You see what happens when a charged particle is experiencing some sort of a revolution. So the moment a charged particle experiences a revolution, it is in fact accelerating, right? And this acceleration should lead to some sort of a release of energy in the form of electromagnetic radiation. So from electromagnetic theory, we know that whenever charged particles accelerate or decelerate, they essentially absorb or release energy in the form of electromagnetic radiation. So if an electron is indeed revolving around a particular nucleus, a positively charged nucleus, and because the electron is negatively charged, it should release energy in the form of electromagnetic radiation, and it should slowly spiral inwards and fall within the nucleus. So what we should actually end up seeing for a certain realistic scenario is that you have the nucleus and then you have the electron, which, because it is revolving around the nucleus, loses energy in a continuous fashion and spiral inwards and fall into the nucleus. And according to calculations, this kind of a spiraling inwards phenomena spiral inwards into the nucleus. This phenomena should happen in a very short interval of time. However, atomic structure has been stable for a long period of time, since almost the origin of the universe. So we have stable atoms in the universe. That means that clearly this is not happening. So therefore, there's something wrong with the Rutherford's model, and not just this kind of a spiraling inwards of a negatively charged electron, but this model also doesn't explain the emission and the absorption spectra. So let me take a small moment to talk about spectra. So whenever we excite some kind of a gas by passing a suitable electric current through it, then we see that the gas starts glowing. And when we look at this radiation coming out of the gas, we find that it is not a continuous distribution of wavelengths, but very discrete, finite, specific wavelengths associated with that particular chemical element. So this kind of a spectra of wavelengths that we observe when we look at the radiation coming out of a gas is known as emission spectra. Similarly, if we pass light through a particular gas medium, then we find that the incident light, some of its wavelengths gets absorbed by the particular gaseous medium, and some of the specific wavelengths are missing, which is known as absorption spectra. So this emission and the absorption spectra are a characteristic of chemical elements, and they are very much discrete in nature, as you can see from the diagrams. And the Rutherford model, apart from the fact that it did not explain the stability of the atom, was also not able to give any explanation as to the discrete spectra in the emission and the absorption spectra of various kinds of chemical elements. Because if the electron has no restriction around the nucleus and there is a continuous sort of a radius of various orbits present, then we should find a continuous emission spectra, right? We should find a continuous emission spectra when we look at the emission spectra of various chemical elements, but we do not see a continuous emission spectra. We see very discrete specific lines corresponding to certain specific wavelengths, which are a signature corresponding to that particular element. So based on these reasons, the Rutherford model was quickly rejected. However, the simplicity of the Rutherford model, that the atom is similar to the planetary model where electrons revolve around the nucleus, became so popular that it is part of our cultural idea of what an atom represents. Now let's move on to the next evolution of this model, which is the Bohr model of the atom. The Bohr model of the atom was given by Niels Bohr, where he combined the classical ideas of physics with some quantum ideas to create an overall semi-classical quantum model of the atom. So let us discuss the Bohr model of the atomic structure. So Niels Bohr combined this classical planetary model of the atom with the ideas of spectroscopy. So we just now talked about the emission and the absorption spectra, where chemical elements, whenever they emit radiation, we look at those radiations, we see that these radiations consists of discrete lines corresponding to specific wavelengths, and these discrete lines of wavelengths are a characteristic of different chemical elements. So Niels Bohr essentially realized that there is some sort of a discreteness that is associated with the atomic transition. So whenever atoms are going from an excited state to a ground state, there is some sort of a transition which is happening, which is discrete in nature and not continuous in fashion. In fact, Niels Bohr was very much inspired by what is known as the formula corresponding to the Balmer series. So Balmer series is a very specific portion of the visible radiation emitted by hydrogen atom. So when you look at the Balmer series, it consists of a large number of discrete and separated wavelengths in the visible spectrum, and Balmer specifically came up with a formula to predict this kind of a spectral series. So Niels Bohr had this idea that quantum mechanics and the principles of quantum mechanics are only manifested in the microscopic domain, but whenever the number of particles becomes large, we end up in the classical domain, then those quantum effects kind of vanish. What Bohr said is that you have this kind of a model where an electron is going around a positively charged nucleus in a circular orbit that constitutes the atom. However, the electron is not in some random orbit, but there are certain kinds of orbits which are allowed. So these are known as stationary orbits. So he borrowed the planetary model of the atom, but instead of having a continuous range of orbits, any orbit being possible, he said that only certain kinds of stationary orbits are possible. And he said that if an electron is in one of these stationary orbits, then the electron's energy would remain a constant in time, and the electron would not release energy and spiral inwards as long as the electron is present in that stationary orbit. And the second point is that he gave the stability condition associated with these stationary orbits. So the stability condition that he provided was that the angular momentum of the electron which is going around the positively charged nucleus is actually an integral multiple of h upon 2 pi or h cut. Now this is a formula that he worked backwards from the application of the correspondence principle to the Balmer series prediction of the spectral lines corresponding to hydrogen. But this is a stability condition that he concluded is true for all these stationary orbits. So the angular momentum is an integral multiple. So n can take the values of 1, 2, 3, 4 and on of h cut. So an atom is essentially a positively charged nucleus according to Bohr with multiple possible orbits around the nucleus. All these orbits correspond to some particular stability condition. So let's suppose for n is equal to 1, you have particular orbit. For n is equal to 2, you have another orbit, and on and on and on. And he said that as long as the stability condition is maintained, you will end up getting a stable atom where the electron remains at a particular configuration with constant energy. And then he tried to explain atomic transitions or the spectra of various chemical elements by coming up with a third postulate in which he said basically that the emission spectra that we just now talked about, in which if you excite some kind of a gas by passing an electric current through it, and then the gas starts glowing and you look at the wavelengths which are emitted by the gas, you do not see a continuous distribution of wavelengths, but you see some very discrete specific wavelengths corresponding to a very specific chemical element. So he said that these wavelengths are emitted whenever some sort of a atomic transition takes place. So for example, if an electron is in an excited state, let's suppose, and it jumps from the excited states to a lower state or the ground level, then an equivalent amount of energy is released in this process, which is equal to the difference in the energy between these two states. So let's suppose there are multiple stationary states corresponding to this particular stability condition, and each one of these states or each one of these orbits have a specific energy associated with them, and these energies are different. So let's suppose this is the initial energy of the configuration and this is the final energy of the configuration. So if an electron jumps from a higher state to a lower state, so atomic transition, then a difference in the energy between the higher and the lower state is actually emitted in the process, thus corresponding to some specific wavelength or frequency which is emitted in that particular phenomena. This third point is very essential because this kind of gives us an idea about the origin of the spectra of various kinds of chemical elements. Whether certain kinds of chemical elements absorb a particular wavelength or whether some of them emit a particular wavelength basically has to do with the signature atomic structure that that particular chemical element has. So when an electron jumps from a higher to a lower state, a particular wavelength or a frequency of radiation is emitted, and when the electron absorbs a similar frequency of radiation, it jumps from the lower to the higher excited state. So Bohr's model of the atom is essentially a combination of the Rutherford's model with some sort of a stability condition which looks something like this, and you can say that this is kind of a semi-classical model in which the atom goes around the nucleus but in specific stationary orbits which satisfies this condition, and whenever an electron jumps between orbits, then there is a certain kind of absorption or emission of an equivalent amount of energy which is equal to the difference in those energy levels that takes place by an emission or absorption of a light photon. However, what I want to focus here in the last part of the video is why is it that this stability condition actually works? Why is it that this particular stability condition arises in quantum mechanics? And an answer to that came 10 years later by de-Broglie. So we have discussed the de-Broglie hypothesis, right? Where we talked about matter waves and where we talked about how motion of electrons is associated with some sort of a motion of a wave that has a particular wavelength that is inversely correlated to momentum. Now those ideas can actually be used to prove why such stationary orbits exist from the perspective of wave-particle duality. So let's look at that. But before we talk about the quantum mechanical reason as to why such kind of Bohr's stability condition works, first let me obtain the general expressions for the energy and the radius of a Bohr atom based on our previous calculation. Alright. So essentially what we have is, here we have the total energy and here we have the velocity of an electron going around in this kind of an orbit in an atom. But now we can apply the Bohr's stability condition. See, Bohr's stability condition says that the angular momentum of a point charge electron, which is basically equal to mvr, m being the mass of the electron, v orbital velocity, r radius, is equal to integral multiple of h upon 2 pi. Here what we can do is we can substitute what velocity that we have obtained here, v, and we can apply it here basically, okay, because this is a v that we have obtained from the classical model of the planetary model of the atom. So if we apply this particular v here, we can get an idea about the radius of this particular stability condition corresponding to a particular orbit. So nh upon 2 pi mv. The radius comes out to be nh upon 2 pi m, and then you have root over 4 pi epsilon mr upon e square. If I take the square of both sides, I end up getting r square is equal to n square h square 4 pi square m square times 4 pi epsilon naught mr upon e square. So here some of the terms will get cancelled out, 4 gets cancelled out, pi vanishes, and then m also vanishes, and r becomes to the power 1 on the left hand side. And finally we can come up with this particular expression that the radius of these stationary orbits basically, or stationary states or stationary orbits, the radius is equal to n square epsilon naught h square upon pi e square. There is also a mass m here. I can write this in terms of h cut. So if I want to write it in terms of h cut is equal to h upon 2 pi. If I write it in terms of h cut, this expression essentially becomes what? This expression essentially becomes n square. So if I have h cut, so here I'll have 4 pi epsilon naught h cut square upon m e square. So the radius of these stationary orbits predicted by Niels Bohr basically follows this particular expression where 4 pi epsilon naught h cut m e, these are all constants, right? And I can actually find out the value of these constants. So if I say that this constants is equal to a naught, this comes out to be n square a naught, where the constants have a value of 0.53 angstrom. You see that corresponding to n is equal to 1, the radius of the very first orbit is 0.53 angstrom, which is known as the Bohr orbit, which is actually the orbit corresponding to the ground state of the hydrogen atom. So therefore the Bohr model successfully predicted the ground state orbit corresponding to the hydrogen atom. We can also figure out a relationship for energy. So if we are interested in figuring out what is the total energy of the hydrogen atom, then we can use this particular expression that we have obtained earlier. So E is equal to, you have minus E square upon 8 pi epsilon naught R. But what is R? R is basically, I should say Rn, because R can have multiple values, right? For n is equal to 1, 2, 3, 4, 5, you can have various radius corresponding to various stable or stationary orbits. So again, so for Rn you will have basically this particular value. So if I just plug in the entire value, then I should end up getting something like n square 4 pi epsilon naught h cut square and m e square. So finally we have an expression for the energy for all these stable orbits, and it comes out to be minus m e to the power 4 32 pi square epsilon naught square h cut square and 1 by n square. This gives you a general idea about the nature of the energies corresponding to the stable orbits. But because all of these are constants, if I calculate all these values, what I actually end up getting is this. I actually end up getting that the energies corresponding to these stationary orbits is equal to minus 13.6 electron volt upon n square. That's it. So this is the expression for the energy of the stationary orbits in the Bohr's model of the atom. And this actually corresponds to the correct result, which is basically for n is equal to 1, you get the ground state energy, which is minus 13.6 electron volt for an orbit having a radius of 0.53 angstrom. Similarly, you can calculate the other sort of orbits also. So if you look at the various kinds of energy levels, let's suppose you have the ground state, you have the first excited state, you have the second excited state, and on and on. So the ground state has an energy of minus 13.6 electron volt. The first excited state has an energy of minus 13.6 upon 2 square electron volt. The second excited state has an energy of minus 13.6 upon 3 square electron volt, and on and on. So you can see that the energies of these stationary orbits which are allowed goes according to 1 upon n square. Now coming to why the stability condition that provided by Bohr actually works, we need to go back to our de-Broglie hypothesis. Okay, so let us do a little bit of a, flashback to memory lane. In one of our previous lectures, we discussed the de-Broglie hypothesis. So the de-Broglie hypothesis essentially arises because of wave-particle duality. So in quantum mechanics, we see that microscopic particles like electrons demonstrate wave-like behavior, like interference, like diffraction. And to explain this, we have what is known as the de-Broglie hypothesis. The de-Broglie hypothesis says that microscopic particles that have a certain sort of a motion or a momentum is also associated with a matter wave, and the matter wave has a certain wavelength, and the de-Broglie hypothesis gives us a relationship between the wavelength and the particle's momentum. Now, what if we apply this kind of a de-Broglie hypothesis to the Bohr's stability condition? Then what we get? We will get an explanation as to why the stability condition works in the first place. Okay, so the Bohr stability condition is angular momentum of an electron around the nucleus is integral multiple of h upon 2 pi, where if I do a little bit of a rearrangement, I take 2 pi left hand side, I end up getting 2 pi r is equal to nh upon mv. Now what is this quantity? H upon mv. H upon mv is nothing but h upon p, right? So this is h upon mv because mv is the momentum of the moving electron. So if I substitute this here, then what do we end up getting? We end up getting 2 pi r is equal to n lambda. What is lambda? Lambda is the wavelength corresponding to the electron's motion around the nucleus in the orbit. And 2 pi r, what is that? 2 pi r is the circumference. So 2 pi r is basically the circumference of the electron orbit, and lambda is the wavelength of the matter wave associated with the electron. What does this mean? It means that when the electron is in a stationary orbit, then it has a certain momentum because of which it has a wavelength. Then that wavelength satisfies this condition where the circumference is an integral multiple of that particular wavelength. It means that, so if I have some kind of an orbit, let's suppose, if I have an orbit like this, and let's suppose this is an orbit around the nucleus, I hope that you can see that, and the electron has a wavelength associated with it, then the circumference of the orbit is an integral multiple of the wavelength. So let me draw a wavelength here, okay? You see that? This is like some sort of a circular standing wave pattern. So the circumference is equal to an integral multiple of the wavelength of the electron, which now tells us why this condition exists in the first place. This condition exists corresponding to those scenarios in which the circumference of the orbit is actually an integral multiple of the electron's matter wavelength. Because in those cases, when the electron's wave essentially forms these circular standing wave patterns, we end up getting constructive interference, because of which we get a stable orbit, because of which we get a stable electronic structure or atomic structure. If we do not get this, if we get a situation in which the circumference is not an integral multiple of the wavelength, let's suppose we have a certain kind of a circumference here and we have some wavelength which is not, let's suppose, an integral multiple of the wavelength, we end up getting destructive interference. Okay, so in one case we have constructive interference, wherever circumference is an integral multiple of the wavelength, and we have destructive interference wherever circumference is not an integral multiple of wavelength, and these orbits do not exist. Only these orbits exist, which are the stationary orbits. So the original problem of the Rutherford model, in which the electron was a point mass negatively charged particles that is supposed to decelerate and release energy and spiral inwards, is avoided by this quantum picture of the electron. You see, in the classical picture, we just have pure particles and pure waves, but in the quantum picture, we have both a sort of a manifestation of the wave nature and the particle nature. And because electrons are essentially waves, if this kind of an integral sort of a relationship is maintained, we get constructive interference and we get stable orbits. So this constructive interference of the electron wave by forming circular standing wave patterns is the stability condition that Bohr actually obtained in his postulate. So basically, the orbit of the electron in a hydrogen atom corresponds to one complete electron wave joined in itself, and thus we can look at the different kinds of stationary orbits possible. So let's suppose we are interested in the ground state orbit, okay, the very first stationary orbit. We can say that it corresponds to one electron wave. If we look at the first excited state, there are going to be 2 electron waves, n corresponding to 2. Then if we have, let's suppose, n corresponding to 4, we are going to have 4 electron waves. And let's suppose for n corresponding to 8, we are going to have 8 complete electron wave lengths. So whenever we're talking about electronic transitions, what we have is various kinds of electronic configurations of electron waves going around the nucleus. And whenever transitions takes place, an electron changes its configuration from one of these to the other. So as you can see, the Niels Bohr model is a combination of the classical picture of the electron going around a nucleus because of electrostatic attraction in the same way that planets go around the sun, but also a quantum mechanical picture in which the electron is a wave and the wave is trying to create constructive interference, and only those orbits survive where the circumference is an integral multiple of the electron's wavelength. And combining these ideas, we have one of the earliest successful models of the atomic structure, which is the Niels Bohr model of the atom. Although this model is only successful for very minority of cases, but this was a very good starting point for our quantum mechanical theory, because the quantum mechanical picture of wave-particle duality can actually explain the atomic structure at the most simplest configurations, which is that of a hydrogen atom. So that is all for today. In the next video, we are going to take a deep dive into various kinds of atomic transitions and the detailed nature of atomic spectra and the various kinds of series that we see when we look at hydrogen atomic spectra. So till then, I am JJ Thomson Model. This is For the Love of Physics. I'll see you next time. Take care. Bye-bye.